everyone, it's been a while. I really missed you all. I've also missed recording new videos. Today I am back with a new educational video. We are going to learn exactly how the nRF24L01 works. So, let's get started. nRF24L01 features frequency 2.4 GHz ISM, industrial, scientific and medical band operation. It provides a 125 channel spectrum between 2.4 and 2.5 to 5 GHz. In this way, it reduces interference by working simultaneously on different channels. By the way, Wi-Fi and Bluetooth operate in the 2.4 GHz band, which is open for general use. Data transmission rates 250 kilobit per second, 1 megabit per second and 2 megabit per second. Short distance communication can be achieved at high speed or longer distance communication at low speed. This is because lower data rates allow for more robust and reliable communication. You can think of it like talking to someone far away. When the person is close, you can speak quickly and quietly and still be understood. But when the person is far away, you need to speak more slowly, more clearly and louder so they can understand you. In the same way, lower data rates make communication more reliable over longer distances. Here we see the configurations with the fastest data rate and the highest transmission power. 0 dBm at 2 megabit per second. This corresponds to the maximum power consumption of the device. Power consumption, power down mode, 900 nA, standby 1 mode, 22 microampere. EX active mode 11.3 mA, RX active mode 12.3 mA. RF24L01 has low power consumption levels of 900 nA in power down mode and 11.3 mA in active mode. Transmission distance 50 to 100 meters in open area. Distances vary for indoor and outdoor use. It generally has a coverage area of 50 to 100 meters. The distance can be increased with the booster antenna. Example nRF24L01 plus PA plus LNA. With the nRF24L01 plus PA plus LNA model, this distance can be up to 800 meters to 1 kilometer in open areas. PA, power amplifier. It means power amplifier. It extends the transmission distance by increasing the signal strength. This amplifier increases the output power when sending the signal, allowing it to reach longer distances. LNA, low noise amplifier. It means low noise amplifier. It keeps noise to a minimum while strengthening the signal at the receiver end. In this way, it allows receiving weak signals more clearly and reduces data loss, especially over long distances. Operating voltage, minimum 1.9 volt, typical 3.3 volt, maximum 3.6 volt. RF24L01 can operate between 1.9 volt and 3.6 volt, typically used with 3.3 volt. It's most commonly supplied with 3.3 volt because this voltage ensures the optimum performance of the module and provides a compatible connection with microcontrollers. Connection type, SPI. It connects to microcontrollers using the SPI, Serial Peripheral Interface Protocol. It supports communication speed of up to 8 megabits via SPI. This means 1 megabyte per second. 8 bits are 1 byte, so we divide 8 million bits by 8, which equals 1 megabyte. Multi-receiver support. 6x pipe address. It supports up to 6 data paths. It allows the transmitter to send data to multiple receivers simultaneously. Networks can be created using pipes. Data packet security. automatic acknowledgement, auto-ACK, automatic retransmission. Data security is ensured through automatic acknowledgement, auto-ACK, and automatic retransmission features. Automatic acknowledgement, auto-ACK. This feature automatically sends an acknowledgement signal to the sender to confirm that the data packet has been successfully received by the receiver. When a data packet is sent, the receiving device sends an ACK signal as soon as it receives the packet. The signal notifies the sender that the data has been successfully delivered. If the sender does not receive this ACK signal, it assumes there was an issue with the transmission and automatically retransmits the packet. Automatic retransmission. This is a feature that automatically resends the data packet to prevent data loss and ensure reliability if the packet does not reach the receiver or becomes corrupted. This process continues for a specified number of attempts or for a certain period. If success is still not achieved, the sender typically terminates the communication or initiates another error handling procedure. Automatic packet processing, CRC, cyclic redundancy check. It can process data packets automatically. With CRC support, it ensures data integrity. Supports packet size from 1 to 32 bytes. CRC working principle. The sender adds a small CRC value to the data packet. This value is generated through a mathematical calculation based on the content of the data. When the data reaches the receiver compares the calculated CRC value with the received one. If the two values match, the data is considered to have been received correctly. If the values don't match, it means the data has been corrupted, and the packet may be requested again. Power control and interference reduction. -18 dBm, 0 dBm. The module's output power can be adjusted between -18 dBm and 0 dBm. FHSS, frequency hopping spread spectrum. It reduces interference caused by other devices. FHSS are not available in the nRF24L01. FHSS, frequency hopping spread spectrum. FHSS means that the module changes frequencies at specific intervals. Instead of using a single channel during data transmission, it jumps between different channels to send data. The nRF24L01 requires manual channel selection and does not implement FHSS. However, FHSS-like behavior can be achieved using microcontroller-controlled software frequency hopping, although it will not reach the speeds achievable with hardware-based FHSS. Modulation, GFS-key. It uses GFS-key, Gaussian frequency shift keying, which provides low noise during wireless data transmission. GFS-key is known for its low noise, high efficiency, and ability to minimize signal distortion. nRF24L01 internal structure. Here we can see some of the pins, their names and what they are used for. At the same time, on the right side, we can also see the block diagram showing the hardware layout inside the chip. Now, I will go through all of them quickly and then move on to the next page. Register map shows register addresses. IREF, current reference. Connect this pin to the ground with a 22 kΩ resistor. ANT1, ANT2, antennas. DVDD, digital supply voltage. IREF provides reference current to internal oscillator for timing. VDD_PA, power amplifier drain voltage. Power amplifier supply voltage. XC1, XC2, crystal oscillator. Here we can see that the chip has a square area of 4 mm. From the pin 1 indicator, moving counterclockwise, the sequence of the 20 pins can be seen. The circular mark on the chips always indicates pin 1. Enhanced shock burst features. 1 to 32 bytes dynamic payload length. 2. Auto packet handling. Preparing the data packet. 3. Auto-packet transaction handling, transmission success check. A. Auto-acknowledgement. B. Auto-retransmit. 4. 6 data pipe multiceiver. I have already explained everything shown in the block diagram in detail on the following page. So we will see how each part works. We will not focus only on GFSK, because this modulation is used for generating wireless signals and reading signals from the transmitter. And the chip already performs this process automatically. I have already explained how SPI works in my previous lesson, so I will not go over it again. Let's check out these abbreviations and see what they mean. I will go through them quickly so you can get the idea before we move on. Glossary of terms. Term, description. ACK, acknowledgement. ART, auto-retransmit. CE, chip enable. CLK, clock. CRC, cyclic redundancy check. CSN, chip select not. ESP, enhanced shock burst. GFSK, Gaussian frequency shift key. IRQ, interrupt request. ISM, industrial, scientific, medical. LNA, low noise amplifier. LSB, least significant bit. LS byte, least significant byte. Mbps, megabit per second. MCU, microcontroller unit. MISO, master in slave out. MOSI, master out slave in. MSB, most significant bit. MS byte, most significant byte. PCB, printed circuit board. PID, packet identity bits. PLD, payload. PRX, primary RX. PTX, primary TX. PWR_DWN, power down. PWR_up, power up. ROIS, restriction of use of certain hazardous substances. RX, receive. RX_DR, receive data ready. SPI, serial peripheral interface. TX, transmit. TX_DS, transmit data sent. SPI timing. The table shows the timing details of SPI communication, including which signals MISO, MOSI, SEK, CS are active at specific clock cycles. It highlights when data is transmitted, received, and when the device is ready to send or capture information. Essentially, it maps the sequence of data exchange between master and slave devices. I won't go into detail here because the following pages also include these two tables, with a more detailed representation available there. Addressing data pipes 05. Each pipe can have up to 5 byte configurable address. Data pipe 0 has a unique 5 byte address. Data pipes 1 to 5 share the 4 most significant address bytes. The LS byte must be unique for all 6 pipes. Table is an example of how data pipes 0 to 5 are addressed. FIFO data flow diagram with SPI. This diagram illustrates the FIFO data flow with SPI communication. Incoming data is stored in the RX FIFO, organized in up to 3 32-byte blocks, and managed by the RX FIFO controller. Outgoing data is placed in the TX FIFO, also with a maximum of 3 32-byte blocks, and controlled by the TX FIFO controller. The SPI command decoder coordinates the transfer of data between the SPI interface and the FIFO buffers, ensuring proper data transmission and reception. Auto acknowledgement. When the MCU preloads an ACK payload into the receiver's TX5 over a specific pipe, and the transmitter sends data to that pipe, the receiver automatically attaches the prepared payload to the ACK packet. So in this case, the receiver is basically saying, yes, I got your message and here is my response at the same time. In this way, the receiver doesn't just acknowledge the message, it also sends its response immediately. On the transmitter side, the ACK payload arrives together with the acknowledgement of the packet it just sent. The hardware writes this data into the RX FIFO and then raises the data ready flag. For the receiver, sending data means simply writing an ACK payload into the TX FIFO. For the transmitter, receiving means reading it directly from the RX FIFO. If the receiver's TX FIFO is empty, the hardware generates a normal ACK without payload. All of this is handled automatically in hardware. There is no need for mode switching on either side. To use this feature, ACK with payload must be enabled on both the receiver and the transmitter. This mechanism saves time and is especially useful for ping-pong style communication. Chip wiring schematic. Here we can see the chip wiring diagram from the datasheet. All connections are detailed in the diagram. The chip is connected and operated according to this diagram. The nRF24L01 chip comes pre-mounted on the circuit, but it is still useful to know its wiring schematic. SPI commands. Command name, command word, binary, data bytes, operation. Read register 1 to 5 ls byte first. This command is used to read data from internal registers. A bits determines which register will be read with read register command. Write register. This command is used to write data into internal registers. A bits determines which register will be written with write register command. This operation is executable only in power down or standby modes. Read RX payload. This command reads RX payload with a length ranging from 1 to 32 bytes. This operation always starts at byte 0, and the payload is deleted from the FIFO after its read. It's used in RX mode. Write TX payload. This command writes a TX payload with a length ranging from 1 to 32 bytes. This write operation always starts from byte 0, and it's used for transmitting data in TX mode. Flush TX. This command flushes the TX FIFO. It's used in TX mode. Flush RX. This command flushes the RX FIFO. It's used in RX mode. It shouldn't be executed during the transmission of an acknowledged. If this happens, the acknowledged package will not be sent. Reuse TX payload. This command reuses the last transmitted payload. TX payload reuse remains active until a write TX payload or flush TX is executed. TX payload reuse must not be activated or deactivated during package transmission. Activate. After executing this command, sending the hexadecimal 73 data activates the following features. Read RX payload with write ECK payload, write TX payload no ECK. When the same operation is repeated, they are deactivated. These features are initially in a deactivated state. Writing to these registers has no effect, and the read operation results in zeros on the MISO. The activate command is executable in standby or power down modes. Read RX payload width. It's used to read the length of the first data in the RX FIFO. The lengths of the data are read one by one and in the order they were received. Each read returns the length of the next data. The read operation is performed with no operation. Write ACK payload. It's used to send a predefined message to the transmitter via the ACK packet. The message to be sent with the ACK is written to the pipe P bits. The P bits ranges from pipe 0 to pipe 5, which corresponds to values between 000 and 101. A maximum of 3 ACK payloads, messages, can be pending. Messages with the same P bits are processed in a first-in first-out FIFO manner. The write length ranges from 1 to 32 bytes. The write operation always starts from byte 0. The ACK payload is used in RX receiver mode. Write TX payload no ACK. Used to send data without ACK. Disables auto ACK when sending data. Used in TX transmitter mode. No operation. No operation is used for read operations. For example, it can be used to read registers, the data received in the FIFO, and data lengths. Register map table. Address, X, mnemonic, bit, initial value, reset value, type, description. 00 config, configuration register. Bit 7 is reserved, readable and writable. Only 0 is allowed. Mask RX.ready, bit 6, initial value 0, type readable, writable. Controls whether the interrupt generated by RX.ready is reflected on the interrupt request pin. When set to 1, the interrupt is masked and no signal is reflected on the interrupt request pin. When set to 0, if the interrupt occurs, the interrupt request pin becomes active low. Mask TX data send and mask max retransmit are the same as mask RX data ready, so I am moving on to the next one. Enable cyclic redundancy check. This feature enables cyclic redundancy check. If any bit in enable auto acknowledgement is set high, cyclic redundancy check is forced to stay high. If all enable auto acknowledgement bits are set to 0 and only cyclic redundancy check is high, the integrity of incoming data is verified using cyclic redundancy check. Cyclic redundancy check length select. Cyclic redundancy check encoding method. 1 byte creates a 1 byte control value. Faster, less reliable, effective for small data. Takes up less space in the data packet. 2 byte creates a 2 byte control value. Slightly slower, more reliable, effective for large data. Takes up more space in the data packet. Power up. Power up provides power to the module or puts it into power down mode. When power up equals 1, the module enters standby mode and becomes ready for data communication. When power up equals 0, the module enters power down mode and data communication does not occur. Primary RX. Primary RX sets the module to either receive or transmit mode. When primary RX equals 1, the module is in receive mode. When primary RX equals 0, the module is in transmit mode. 01. Enable auto acknowledgement. Enhanced shock burst. Enable auto acknowledgement pipe 0. Enable auto acknowledgement pipe 0 enables the auto acknowledgement feature for data pipe 0. The other pipes have the same properties, so I'm not reading them and moving on. 02. Enable receive address. When auto-acknowledgement is enabled, it's essential to activate P0 because acknowledgement packets are always transmitted through data pipe 0. Enable receive P0 activates receiver data pipe 0 for communication. 3. Set up address width. Address widths. Address width is used to prevent collisions when multiple devices are operating in the same radio frequency environment. Longer addresses reduce the chance of collisions by providing uniqueness and preventing false matches. Collision is when multiple devices use the same address at the same time or send data simultaneously, causing their signals to interfere with each other. In this case, the receiver may mistakenly consider an incorrect address as valid. 3-byte address collision probability is 1 in 16.7 million. 5-byte address collision probability is 1 in 1.1 trillion. If two devices in a network use the same address, it results in an address collision. Such collisions can lead to devices misunderstanding each other and data being sent to the wrong destination. To prevent this, devices are configured with unique addresses. Statistical probability decreases. As the address length increases, the probability of two devices using the same address decreases exponentially. Advantage in dense networks. In environments with more devices, short addresses increase the risk of collisions, while longer addresses reduce this risk to nearly zero. Devices must have the same address width configuration for communication to occur. If the sender and receiver have different address widths, communication will not happen. As the address width increases, energy consumption also increases. However, this difference is typically very small and negligible in terms of the overall system energy consumption. Longer addresses mean that more data must be processed by both the sender and the receiver during communication. Since the address field occupies more space in each transmitted data packet, the total transmission time also increases slightly. The receiver reads and checks more data to verify the address. Address width, receiver, transmitter, address length, 00, not used, 01, 3 bytes, 10, 4 bytes, 11, 5 bytes. If the address width is below 5 bytes, ls byte is used, common for all data pipes. 4. Setup retransmission, automatic retransmission. Auto retransmit delay. Devices are ensured to transmit data at different times, preventing collisions. A short auto retransmit delay duration shortens the waiting mode time and can increase the likelihood of packet collisions. In real-time data transmission or networks with fewer devices, fast retransmission may be necessary or sufficient. The auto retransmit delay value represents a 4-bit value and provides 15 different timing options, including 0. 250, this is the microsecond delay added for each increment step. Plus 1, this addition is made because the auto retransmit delay value starts from 0. Auto retransmit delay value plus 1 times 250 equals microsecond delay time. The decimal equivalents of the binary numbers are the auto retransmit delay values. Here we can see the calculation method. The binary number 1011 corresponds to 11. Adding 1 to 11 and multiplying the result by 250 gives the auto retransmit delay time. The delay defined between the end of the one transmission and the start of the next transmission. Automatic retransmission counter. During data transmission, transmission errors or losses may occur. Automatic retransmission counter helps the transmitting device to compensate for these transmission errors. If no auto-acknowledgement signal is received from the receiver, if auto-acknowledgement fails, the transmission is considered to have failed. Automatic retransmission counter determines how many times the data will be retransmitted in case of a transmission failure. The decimal equivalent of binary values determines the number of retransmission attempts. Here we can see some examples. 0000 retransmission disabled. 0001 1 retransmission attempt. 1111 15 retransmission attempts, maximum value. The number of transmissions can be determined by converting the binary numbers to their decimal equivalents. The module will attempt retransmission up to the specified count, and if it still fails, the transmission is considered complete. 5. Radio frequency channel. Radio frequency channel sets the frequency channel on which the nRF24L01 operates. The channel adjustment is made using the formula F0 equals 2400 plus radio frequency channel megahertz. A total of 126 channels can be used, including channel 0 and channel 125, and all the channels in between. All channels in the closed range between 2.4 GHz and 2.5 to 5 GHz are part of the general purpose industrial, scientific and medical band. All bits from 6 to 0 are used to adjust the channel. Channel 0 2.400 GHz and channel 1 2.401 GHz are commonly used channels and may cause more frequency overlap or interference with surrounding devices. Here we can see the two channels that cannot be used and their corresponding bit values. Channel 126 is unavailable, channel 127 is unavailable. Each channel is spaced 1 MHz apart. 6. Radio frequency setup. Phase-locked loop. Forces the phase-locked loop signal to activate. It's only used during testing. Radio frequency data rate is a parameter that determines the data transmission rate in a wireless communication module. This parameter defines how many bits of data will be transmitted per second over the radio waves. As the data rate increases, the distance shortens. Rate of data transmitted over the air. If this register is set to 0, the data rate is 1 megabit per second, which is equal to 125 kilobyte. If it's set to 1, the data rate is 2 megabit per second, which is equal to 250 kilobyte. Radio frequency power is the parameter that determines the amount of power transmitted through radio waves. It represents the power of the transmitted signal and is commonly measured in dBm. Here we can see the power range. Sets the radio frequency output power in transmitter mode. Low noise amplifier high current allows the low noise amplifier to consume more power in the receiver circuit, enabling stronger signal amplification. Low noise amplifier radio frequency signals are usually very weak. The low noise amplifier efficiently amplifies the incoming low signals to a higher level, resulting in a clearer and stronger signal. Low noise amplifier gain. The gain of the low noise amplifier shows how much it increases the signal, and it's typically measured in decibels, allowing the signal to reach the receiver more powerfully. 7. Status. The status register is serially shifted out on the mesopin in parallel with the SPI command word applied to the mesopin. Receiver data ready. Data received receiver FIFO interrupt. The interrupt bit is asserted when new data is received. Send 1 to clear the bit. Transmitter data send. Data sent transmitter FIFO interrupt. The interrupt bit is asserted after the packet is transmitted. If auto-acknowledgement is enabled, it does not assert until the acknowledgement signal is received. Send 1 to clear the bit. Maximum retransmission. Maximum transmitter retransmission interrupt. If the maximum retransmission interrupt bit is asserted, it must be cleared to allow communication to continue. Send 1 to clear the bit. Received pipe number. The pipe number through which the current data reaches to read from receiver FIFO. 000 to 101 data pipe number. 110 not used. 111 receiver FIFO empty. Received pipe number indicates the pipe number of the data at the top of the FIFO, ready to be read. When new data is added to the FIFO, received pipe number doesn't change immediately. It only updates when a data is read. The FIFO preserves the order of incoming data, ensuring that the data is processed with the correct pipe information. Transmitter full. Transmitter FIFO full flag. When this flag is 1, transmitter FIFO is full. Otherwise, when it's 0, transmitter FIFO has available space. 8. Observe transmit. Packet loss counter. Counts lost packets. Packet loss counter measures the total number of lost packets that couldn't be delivered to the destination despite retransmission attempts. Packet loss counter only increments when all retransmission attempts fail. The counter is protected against overflow. It increments up to 15 and remains at the maximum until it's reset. The counter is reset by writing to the radio frequency channel register. Automatic retransmission counter is the counter for failed retransmission attempts. Automatic retransmission counter increments when a transmission attempt for a packet fails. As retransmission starts, automatic retransmission counter increases by 1 for each failed transmission. The counter is reset when transmission of a new packet starts. 9. Carrier detect. The carrier detect operates in receive mode. The carrier detect is set high when a radio frequency signal is detected in the frequency channel in receiver mode. Otherwise, it's low. Carrier detect in the RF24 hardware is designed according to FSK modulation and performs signal control accordingly. To securely detect the signal, it must be FSK modulated, but other signals can also be detected. The detected signal is filtered based on frequency band, energy level, signal time continuity, modulation type, and pattern before being presented to the carrier detect register. When the radio frequency signal is present for 128 microseconds, the carrier detect will be high. In the enhanced shock burst mode, it's recommended that carrier detect be used only when the primary transmitter device cannot transmit packets. When the maximum retransmit interrupt occurs or packet loss counter indicates a high packet loss rate, the carrier detect can be controlled by switching to primary receiver mode. Here we can see the wait time. If carrier detect is high, this means there is jam condition, high interference, so the frequency channel must be changed. If the carrier detect is low, if the nRF24L01 receiver device is out of range or interference with broadband signals such as wireless local area network, the same frequency channel can be used. However, the record of the old lost packets in packet loss counter may need to be cleared to avoid confusion. Packet loss counter is cleared by fake write, same channel, or real write, different channel, to radio frequency channel. A. Receive address P0. Receiver address of data pipe 0. Maximum length is 5 bytes. The least significant byte is written first. The byte length defined in setup address bit is used. Example address: DD is the least significant byte. C. Receiver address pipe 2. Receiver address of data pipe 2. Only the ls byte is written. The most significant bytes are equal to the bytes of receiver address pipe 1. 10 transmitter address. The transmit address is set to identify the receiver, only used for primary transmitter devices. The least significant byte is written first. Auto-acknowledgement information is received via receive address pipe 0. Therefore, in a primary transmitter device with enhanced shock burst auto-acknowledge feature enabled, set the receive address pipe 0 address to this address for automatic acknowledgement. Receive payload with pipe 0. Receive payload with pipe 0 is used to set the expected data length on the receiver side. The number of bytes on the receiver side in data pipe 0, 0 to 32 bytes. 0 pipe is not used. Excess data, extra bytes is discarded. Truncation, only data up to the length specified by receive payload with pipe 0 is received. Insufficient data, if less bytes than specified is received, the remaining bytes is filled, padding, with zeros. Outside the defined lengths, tracking is difficult and potential issues may arise. TX reuse. Reuse last transmitted data packet when set high. The packet will be retransmitted repeatedly as long as the CE pin is high, until the transmission is successfully acknowledged. The transmit reuse flag is set using the SBI command reuse transmit payload, and it can be cleared with the SBI commands write transmit payload or flash transmit. Once the transmission is successfully acknowledged, the transmit reuse flag is automatically cleared. Transmit full. Transmit FIFO full flag. If transmit FIFO is full, the flag is set to 1. If there is space available in transmit FIFO, the flag is set to 0. 1. Transmit FIFO full. 0. Available space in transmit FIFO. Transmit empty. Transmit FIFO empty flag. If transmit FIFO is empty, the flag is set to 1. If transmit FIFO contains data, the flag is set to 0. 1. Transmit FIFO empty. 0. There is data in the transmit FIFO. ECK payload, transmit payload, receive payload. Not applicable, explanation. In tables, NA stands for not applicable. It means that the item does not have a standard value, address, or setting in that context. For example, some registers like ECK payload or transmit payload are marked as not applicable in the register or address columns. This does not mean they cannot be used. Rather, they are accessed or written only via specific SBI commands, not through a normal memory address. So when you see not applicable, just remember it refers to registers that require special command handling, and you should follow the instructions for writing to them as explained. These have already been explained in the previous images. Dynamic payload pipe 0. Enables dynamic payload length for data pipe 0. Requires enable dynamic payload and enable auto acknowledgement pipe 0. Feature register. Enable dynamic payload. Enables dynamic payload length feature. Enable ECK payload. Enables payload with ECK feature. Enable dynamic ECK. Enables the write transmit payload no ECK command. nRF24L01 uses SPI mode 0, SPI timing read operation, SPI timing write operation. SPI timing. We have seen this on the previous page and I said that there is a more detailed demonstration on the following page. Shows the resistor pool and capacitor load that are referenced in the SPI timing parameters. The values for resistor pool and capacitor load shown in the timing table are example values that were used during the tests, measurements. If you don't understand these timings, you can watch my SPI lesson for a more detailed explanation. Power amplifier control. The power amplifier control is used to set the output power from the nRF24L01 power amplifier. In transmitter mode, power amplifier control has 4 programmable steps. See table. The power amplifier control is set by the radio frequency power bits in the radio frequency setup register. SPI radio frequency setup. Radio frequency output power. DC current consumption. As power increases, current consumed also increases. Power consumption. The low noise amplifier control is used in the nRF24L01 to increase receiver sensitivity by consuming more current. In receive mode, there are 3 data rates for nRF24L01 Plus and 2 for nRF24L01. See table. Use to select data rate on nRF24L01 Plus. Bit 5 equal radio frequency data rate low, and bit 3 radio frequency data rate high. If radio frequency data rate low equal 1, then radio frequency data rate high equals 0, and this selects the 250 kilobit per second mode. Left, bit radio frequency data rate low. Right, bit radio frequency data rate high. Modes 1, 0, 250 kilobit per second, 0, 0, 1 megabit per second, 0, 1, 2 megabit per second, 1, 1, reserved, not used. The low noise amplifier control is set by the low noise amplifier high current bit 0 in the radio frequency setup register. The low noise amplifier high current bit is obsolete for nRF24L01 Plus. Because the low noise amplifier is already optimized for high sensitivity, so no extra high current mode is needed. Here we can see bit 5, which is only for the nRF24L01 Plus. Low noise amplifier low current and low noise amplifier high current are not applicable for the Plus version. The current consumptions for the Plus version are written separately and indicated in parentheses. As the data rate increases, the power consumption also increases. Operational modes configuration. Here we see a table related to mode transitions. By setting the bits indicated in the table, you can switch between the specified modes. When chip enable is held high for 10 microseconds, it performs a single level transmission in transmitter mode. If chip enable is held high for a longer period, the transmitter FIFO is completely emptied, and the device switches to standby 2 mode. This table shows the transition times between modes. Using an external oscillator, the duration is reduced. DC characteristics: digital input pin, digital output pin. These tables indicate the levels of high and low input and output signals. A. If the input signal greater than 3.6 volt, the VDD of the nRF24L01 must be between 2.7 volt and 3.3 volt. So it has a nominal value of 3 volts with a plus or minus 10% tolerance. Power on reset. A. Measured from 0 volt to 1.9 volt. B. Measured from the moment VDD reaches 1.9 volt until the reset process finishes. This table provides power ramp-up time and power on reset time. Here we see the module with the chip pre-installed. The chip itself occupies exactly 4 square millimeters. I will use the ESP32 to send commands to the nRF24L01 module. Here we will see how to connect the two modules. The ESP32 includes a hardware SPI interface. This means the nRF24L01 is connected using the predefined hardware SPI pins, MISO, MOSI, and SCK. The CE and CSN pins can be assigned to any GPIO pins we choose. We can also use software SPI, which allows us to define all the pins manually. Hardware SPI is faster than software SPI. However, with a module like the ESP32, it's possible to achieve hardware level speed even while using software SPI. With a well-optimized codebase, this can be accomplished. Since I am using my own custom written library, I can get very close to hardware SPI speeds. I'm using my own software SPI, but I will still use the pins that hardware SPI uses. I will only change the CE and CSN pins. These pins can also be reassigned in hardware SPI. By default in hardware SPI, CE is usually set to 4 and CSN to 5. Here I have written Arduino code to make two nRF24L01 modules communicate with each other. These codes belong to my own library, so you won't be able to find them online. I won't be explaining the commands here again, because I have already gone over each one of them in detail earlier in the video. So everything you need to know about how the commands work has already been explained. With the code on this page, I am going to make the two nRF24L01 modules play a LED ping-pong game. So, let's get started. This project involves high voltage 220 volt. High voltage circuits are extremely dangerous and can cause serious injury or death. If you don't have sufficient technical knowledge and experience, don't attempt to build or test this circuit. Always use proper insulation, safety equipment, or work under expert supervision. Here we see the wiring diagram of the transmitter circuit that I will use to remotely turn on a 220 volt light bulb. I added the control LED to monitor how long it takes for the bulb to turn off. I am using the input pull-up method to detect button activity. When the button is pressed, pin 22 will become active low, and the ESP32 will write the data to the nRF24L01 to be transmitted. After the transmitter nRF24L01 delivers the message to the receiver nRF24L01, the receiver will send the signal to turn on the bulb and activate it through the relay. Here we see the wiring diagram of the receiver circuit. After the receiver gets the signal, the ESP32 sends a 3.3 volt signal from pin 22 to the base of the BC548, which then drives the relay using the ESP32's 5 volt rail. I set the relay's active duration to 10 seconds in the ESP32 software. Once the time runs out, the ESP32 stops sending the base signal to the BC548 returning the relay's normally open pin from its active state back to its default state. In other words, the connection to the bulb is cut and it turns off. Here you can see the code for both the transmitter and the receiver, along with their explanations. Since software is a separate topic, I won't go into detail here. Still, those who have watched the video from the beginning until now will get at least a rough idea of how the code works just from the names of the variables and functions. Those who don't have any programming knowledge can watch my software lessons. Now, let's light up the bulb. In this section, I will run the motor using wireless communication with the nRF24L01. The transmitter circuit is the same as the transmitter circuit from the previous step. I only removed the control LED from the circuit. Here you can see the receiver side circuit. I calculated all the components in detail and configured the circuit to operate with the most suitable values for 12-volt switching. Of course, with additional components, it's possible to make it faster and better, but since this video is not specifically about motor driving, I won't go into those details here. The power supply I'm using in the circuit is not fully compatible with the motor. But since I'm only using it for testing, I won't be running the motor continuously. For long-term operation, you must use a power supply that matches the motor's requirements. Here you can see the software code for both the receiver and the transmitter. Normally, electric motors are controlled using soft start PWM motor driving algorithms. However, since this video is not focused on software, I avoided adding more code, which would only complicate the topic and make the video longer. For that reason, I didn't use those PWM control codes here. Now I'm going to pull the ice cream container, where I attach the string, using the electric motor by pressing the button remotely. Alright then, let's get this done. If you have watched this far, it means we have not only learned about the nRF24L01, but also a significant part of wireless communication. At this point, you now have enough knowledge to write your own library for the nRF24L01. There are definitely advantages to using a library you wrote yourself. For example, when needed, you can easily add or modify any structure you want. However, there are also many highly developed libraries already available on the market. Of course, writing a library requires patience and time. It also requires strong software skills and solid technical knowledge. For instance, in my current library, excluding examples, I have 32,531 characters and 1,389 lines of code. With the examples included, the total reaches 45,146 characters and 1,773 lines of code. The software is quite complex and requires good focus. These examples can be anything, such as the two-way communication test, like the ping pong game we saw earlier, turning on a light, or driving a motor. Here is what the library I wrote looks like. Today we explored the great capabilities of a very tiny chip, the nRF24L01. All the features I have explained over the past hour are hidden inside a small 4mm integrated circuit. And if we were to look deeper into its inner world, we will see a structure that would be impossible to fully describe. Many of us tend to think that big things only happen in big spaces. But in reality, that's not how it works. Impressive things are born in small places when small pieces come together. Something that looks small is often thought to be ineffective, but scale is not what truly matters. Everything resembles each other because everything grows by combining with something else. So what then is the true meaning of big? Well, I call that infinity. An infinity we carry inside us and one that also exists around us. When we try to understand everything and look at it with a deep sense of appreciation, we realize that we are part of everything, forming a greater whole. And at that moment, being small or big no longer matters, because everything gains meaning when we become a part of it. If everything is a part of everything else, and we are part of it too, then how can the nRF24L01 be insignificant if it's part of us as well? We have come to the end of another lesson. Thanks for watching. Hope to see you again. Take care. Bye bye.